Hello students, in this video we're going to solve some problems about fixed axis rotation. So in this case our first problem is a track star runs 400 meters race on a 400 meters circular track in 45 seconds. So what is the angular velocity, assuming a constant speed? So let us analyze, how we solve this problem. So we have a circular track that is going to be this track over here, okay? And the circumference of this circular track is equal to 400 meters, right? Now, what we know? We know that circumference is equals to 2 times pi times the radius of the circle. So this is how we find the circumference, right, of a circle. Now, if we solve for the radius, we know that radius will be equal to the circumference over 2 pi. That's why I am solving for the radius. Because to find the angular velocity, I need to know the radius, because we know that the linear velocity is equal to the product of the angular velocity times the radius. So if I solve for the angular velocity, I have that angular velocity is equal to linear velocity divided by the radius. Okay? Now, what is, in this case, the linear velocity? The linear velocity is distance divided by the time. So the distance is the circumference divided by the time, right? So if now I substitute here in the formula of angular velocity, the values of v, or the expression of v of the linear velocity and the radius, we get that the angular velocity is, as we said, angular velocity is a linear velocity, so it's c over t divided by, in this case, the radius, so the radius is c over 2 pi. Of course, I will be able to simplify the circumference here, so we get that the angular velocity is equal to 2 pi over the time, right? So it would be 2 pi over 45 seconds. And if we perform the division here, we get that the angular velocity would be 0.14 radians per second. So my question that was, what is the angular velocity assuming a constant speed? The angular velocity assuming a constant speed is 0.14 radians per second. In the next problem, they say that the angular velocity of a rotating rigid body increases from 500 to 1,500 revolutions per minute in 120 seconds. So they ask you what is the angular acceleration of the body and through what angle does it turn in these 120 seconds. So well, the first we have to remember, for the first part of the question, is that the angular acceleration would be equal to the variation in the angular velocity over the variation in time, right? Now, what we know in this case, we know the number of revolutions per minute. So if I want to find, the angular velocity given the number of revolutions per minute, I have then to make some unit conversions. So let me show you something. I'm going to start using, the revolutions per minute to find the variation in angular velocity, and later I'm going to do the conversions. So I'm going to say 1,500 revolutions per minute minus 500 revolutions per minute over 120 seconds. So of course this is 1,000 revolutions per minute, and then instead of RPM I'm gonna write revolutions per minute like this. you know, divided by 120 seconds. Now, I will convert these revolutions per minute into radians per second. So I'm going to say that these 1000 revolutions per minute times 1 minute that have 60 seconds. Here I'm converting into the minutes into seconds times 2 pi radians that I have in each revolution, right? Okay, all this will be divided by the 120 seconds, right? So now we are going to show you how we cancel the units. So I will cancel these revolutions with the revolutions over here. I will simplify these minutes with these minutes over here. So I'm going to have radians per seconds, and radians per second, you know, is the unit that I am expecting to have here, right? Okay, so radians per second is the unit I'm expecting. So now we can multiply 1000 times 2 pi. That is going to give you 2000 pi. And of course, these 120 seconds, you flip it to multiply. So it will be the product of 60 seconds times 120 seconds. So that would be 7,200 seconds squared, right? And if you divide 2000 pi over 7,200, that is going to give you 0.87 radians per second squared, and this will be in this case my angular acceleration. In the second part of the problem, they say to what angle does it turn in these 120 seconds. So we know that the angle will be to the initial angle here plus the initial angular velocity times the time plus 1 over 2 the angular acceleration times the square of the time. I will take this initial angle equal to 0, you know. So now I have, you know, my 500 revolutions per minute. That is my initial angular velocity. I will do the conversion right now here. So times 2 pi per radian. Sorry, 2 pi radian per revolution. My mistake. 2 pi radian per revolution times 1 minute 60 seconds. Of course, times the time, that is 120 seconds, plus 1 over 2, the angular acceleration we found, that was 0.87 radians per second squared times the square of the time. You know that the square of the time is, in this case, 120 seconds squared. Okay, so of course, when you analyze, you know, the units here, you see how you will, in this case, simplify the seconds with the seconds. You will simplify the revolutions with the revolutions. You will simplify the minutes with minutes here. So basically, your unit will be in radians, right? And it's exactly the same thing over here because you have seconds squared that is gonna cancel, you know, with the seconds squared we have here below. So this would be again in radians. So your output unit here is radians, and that makes sense, of course, because we're talking, you know, about angle. So when you do the calculations, you know, of course, you must multiply all this part over here. You will get this is approximately 12,547 radians. This is not the only formula you can use to do this calculation of the angle, right? There are other formulas that you have uh, in your book that you can use also to calculate, uh, the angle. Because you have formulas, that are in terms of the initial and final angular velocity and uh, the angular acceleration and the variation in the angle and others. So I recommend you to go over those other formulas, that are in your book corresponding to this part, and try to solve this same exercise in, any of other those formulas. Look at the next question, the next exercise. It says that a man stands on a merry-go-round that is rotating at 2.5 radians per second. If the coefficient of friction between the man's shoes and the merry-go-round is mu sub s equals 0.5, how far from the axis of rotation can he stand without sliding? It's a very interesting problem. So basically here, if we make a diagram of the problem, we have the merry-go-round here, these have some radius, of course, right? And I have the guy here standing at a position, there is D from the center of rotation, you know, and then when you analyze, as this is rotating, uh, if we have no force other than the centrifugal force, and remember that the centrifugal force is a fictitious force that is equal in magnitude to the centripetal force. The centripetal force points toward the center of rotation. The centrifugal force just points just away from the center of rotation. The problem here is that if the centrifugal force that is equal in magnitude to the centripetal force is greater than the uh, force of friction, then in that case, uh, the guy is going to slide down, or he's going to slide out of the merry-go-round. So the question here is to say, that the force centrifugal at the end is have the same magnitude of the centripetal force. So the centrifugal force here should be equal to the force of friction. So only when there is a balance between those forces, right, is that I have in this case that the guy is now going to slide out of the merry-go-round. Now we know that the centrifugal force that is equal to the centripetal force is equal to the mass times the centripetal acceleration, while the force of friction is equal to the coefficient of friction times the normal force, right? Now, this centripetal acceleration, we know that is equal to the square of the linear velocity divided by the distance, from the center of rotation. And I'm going to take in r here as variable because I'm going to say that r is just the total radius of the merry-go-round, but I'm going to take a d because d is, what I call the distance, or how I call the distance from the person that is standing there on the merry-go-round and the center of rotation. So I'm going to say b squared over d, right? So remember that d is just the distance from the center of rotation. Now this should be equal to mu sub s, and now we know that the normal force is equal to the weight of the person and is equal to the product of the mass times the gravity. So we can simplify the masses here, right? So now I know, that this linear velocity is equal to the product of the angular velocity times the distance d, that this person is from the center of rotation. So if p is the linear velocity, the tangential velocity of this guy here, okay, respect the center of rotation, of course, then I will replace this by the product of the angular velocity times the distance d, right? So I can say that w times d square over d is equal to mu sub s times gravity. So this is w squared, d squared over d is equal to mu sub s gravity. I'm going to simplify d here. So I get w squared d, is equal to mu sub s gravity. So I'm now ready to calculate this. So the distance, that this guy could be from the center of rotation without sliding would be equal to mu sub s times the gravity divided by the square of the uh, mm, angular velocity. So when I substitute now the values here, I say that the distance that this guy can be from the center of rotation without sliding, would be mu sub s, that is 0.5 with no dimensions. Remember that the coefficient of friction have no dimensions, times 9.81 meters per square seconds divided by 2.5 radians per second square. That this is, the angular velocity of the merry-go-round. So we can say that d in this case would be 0.78 meters. So without sliding, this guy can just stand 0.78 meters from the center of the merry-go-round. Just only, by the equality or the relation between the centrifugal force and the force of friction, right? So it's a very, very interesting problem, this one. So I hope, that is going to help you to understand better the action of the centrifugal forces. Look at the next problem. In the next problem, they say that a baseball pitcher throws the ball in a motion where there is a rotation of the forearm about the elbow joint, as well as other movement, right? If the linear velocity of the ball relative to the elbow joint is 20 meters per second at a distance of 0.480 meters from the joint, and the moment of inertia of the forearm is 0.500 kilograms meter square. So what is the rotational kinetic energy of the forearm? So let us make a very quick diagram here. So here we have the elbow joint, and then here we have the ball, and we're throwing the ball with a linear velocity, a tangential velocity of 20.0 meters per second. Now the length of the forearm is 0.480 meters, right? So what we have to do, we have to find the rotational kinetic energy of the forearm. So what is the expression to find the rotational kinetic energy? We know that the rotational kinetic energy is equal to 1 over 2 the moment of inertia times the square of the angular velocity. We know the moment of inertia because it was given here, that is 0.500 kilograms meter square, but I don't know the angular velocity, so I need to find the angular velocity. Nevertheless, I know the linear velocity, and I know the distance from the elbow joint, to the ball. So I know that if my linear velocity is the product of the angular velocities times the distance, right? If I solve for the angular velocity, is equal to the linear velocity divided by the distance, So in this case, this would be 20 meters per second divided by 0.480 meters. So that would be equal to 41.7 radians per second. So this is just the angular velocity here. Okay, so once I know that angular velocity, to calculate the rotational kinetic energy will be very easy, because this rotational kinetic energy will be 1 over 2 of the moment of inertia, that is 0.500 kilograms meter square, times the angular velocity, that is 41.7 radians per second square. And if you do the calculations, you will find that this is approximately 435 joules. So that would be, in this case, the rotational kinetic energy of the forearm. In this problem now, we have that a uniform rod of mass 1 kilogram and length 2 meters is free to rotate about one end. If the rod is released from rest at an angle of 60 degrees with respect to the horizontal, they say what is the speed of the tip of the rod as it's passed through the horizontal position. So we want to find, what is going to be the speed of this rod over here, sorry, when it's passing through the horizontal position. So the first we have to remember is that the moment of inertia of a thin rod about a perpendicular axis that passed through the end would be 1/3 of the mass times the square of the length of the rod. This is the formula to find the moment of inertia. Now, what else is important here? Well, we have that the horizontal position, the negative variation of the potential energy will be equal to the variation in the kinetic energy, right? So this would be negative delta U would be U initial minus U final, and delta K would be K final minus K initial. Of course, the final potential energy when it's passing through this point would be 0, because the height of the center of mass respect the horizontal, is 0, right? So UF is 0. And we know that the initial kinetic energy is also 0, because they say that this is starting from rest. Okay, so we have that the initial potential energy will be equal to the final kinetic energy. Now, to find the initial potential energy, we need to find what is the height of the center of mass of this rod, above the horizontal. So we need to find this distance over here. And of course, right, if this is L is just the length of the rod, right? The center of mass is at L over 2 from the center of rotation. If we have an angle of 60 degrees, then of course this height here is related to the angle through the sine function. So this would be basically here L over 2 sine of 60 degrees, right? So now I know that the potential energy will be the product of the mass of the rod times the gravity times L over 2 sine of 60 degrees. And then we have the kinetic energy, but it's going to be the kinetic energy of rotation. So it would be 1 over 2 the moment of inertia times the square of the angular velocity. Now, of course, we know the Uh, in this case, we know the angular velocity, and we can calculate uh, also the linear velocity. So we can say in this case, let's see, because let me read again. The problem uniform is rotating with respect to the horizontal speed, right? Now we can calculate. Okay, we have to calculate this angular velocity over here. Sorry, I got lost for a second. So we have to calculate now because we want to know what is the speed of the tip of the road, when passed to this position. So now we need to find, this angular velocity. So basically what we want to try to do now is to calculate the angular velocity. So if I solve for the angular velocity, I'm going to have that 2 times mass gravity L over 2 sine of 60 degree equals I times W squared. So you simplify here uh, the factor 2, so you get mass gravity L sine of 60 degree divided by the moment of inertia is equal to W squared. Now we know that the moment of inertia is 1/3 of the mass times the length squared. So I can say the mass gravity L sine of 60 degree divided by 1/3 mass L squared. So we cancel the mass out here. We simplify this L with this one, right? So we're gonna get now, of course, this is equal to W squared. So we're gonna get now, the W would be the square root. We flip these three, so we get 3 gravity sine of 60 degree divided by L. So you substitute the values here, and you're gonna have the angular velocity, is 3 times 9.81 meters per square seconds times the sine of 60 degree, or divided by the length, right? That is 2 meters. So we have now that the angular velocity you calculated is 3.57 radians per second. So I know now the angular velocity, of the road when it's passing through this point over here. So what I want to find now is the speed of the tip, of the road as passed to that position. So now I know that, of course, the speed is equal to the product of the angular velocity times the length, right? So it would be equal to the angular velocity, that is 3.57 radians per second times the length, that is 2 meters. So we have that the linear velocity in this case, or the speed in this case, is 7.14 meters per second. So when this road is passing through this point over here, its tangential velocity, will be 7.14 meters per second. It's going to be pointing downwards, right? If we're talking in terms of a speed, this would be 7.14 meters per second without direction, of course, because it's a speed. The last problem I want to show you, is a problem about torque. So they say to calculate the torque about the z-axis, that is out of the page at the origin of the following figure. Given that the force 1 is 3 newtons, the force 2 is 2 newtons, the force 3 is 3 newtons, and the force 4 is 1.8 newtons. So what we know that if we have here, a bar, and there is here a center of rotation, you know, and there is a force here that is perpendicular to this bar, and this bar have ln L, the torque will be the product of the force times L. So we need a distance L from the center of rotation to the force to have a torque, right? When we have a force passing through the center of rotation, in that case, the torque will be zero, right? So this is something we have to keep in mind. Now, if the force is not a 90-degree respect the bar, right? Like this, we're going to have two components, of course. One component that will be horizontal of this force. So let me call this Fx, right? Let me say that this is the force F. And then we're going to have another component here that will be let me say Fy, right? And Fy will be the component doing torque. Fx is not doing torque respect this point because it's passing through the point. The line of action of the force is just passing through the point. So Fx is not doing torque, and Fy, of course, is doing torque. So now depends, on the angle, okay, to find uh, the magnitude of the force Fy. Well, after understand these elements about torque, let me solve the exercise. So we have a force F2, that is 2 meters from the center of rotation, or from the origin of this coordinate system, and there is an angle of 30 degrees respect the horizontal. So only the horizontal component of the force F2 will be doing torque. The vertical component of the force F2 is not going to do torque. The force F3 is not doing torque because it's passing through the point respect we are calculating the torque, right? The force F1 is perpendicular to the bar, right? So just the product of the force F1 times the length of this bar over here gives the torque respect this point, and the force F4 has 20-degree, respect the vertical. So only the y component of this force F4 will be doing torque respect this center. The horizontal component will be passing through the center, so it's not going to do torque. So if I want to find the resultant torque, I'm going to assume, that when the torque is counterclockwise, it's going to be positive. So I'm going to say that the resultant torque is equal to, let me start with the force F2 here. So I'm going to say the distance from F2 to the center is 2 meters. So I say 2 meters times the force F2. And well, in this case, is the horizontal component of the force F2. So in this case, the horizontal component will be F2 cosine of 30 degree. So it is F2 cosine of 30 degree. And the torque that is done by the force F2 is counterclockwise, so I'm going to take this torque positive. Now minus, because the force F1 is doing a torque that is clockwise, so I'm going to take it as negative, right? So I'm going to say minus, in this case, 3 meters times the magnitude of the force F1. And also minus, so the force F4 is also doing a negative torque because it's making this to rotate, clockwise. Okay, so we know that I'm missing something here. That is that the distance from F4 to the center is also 2 meters. So now we know, that the torque due to F4 is 2 meters times F4, and then is the vertical component, so is cosine of 20 degree. Well, now we know that the torque resultant is equal to 2 meters times 2 newtons cosine of 30 degree minus 3 meters times F1, that is 3 newtons, minus 2 meters times F4, that is 1.8 newtons cosine of 20 degree. So you do the calculations there, you get that the resultant torque will be equal to negative 8.92 newtons meter. So I got a negative sign because is counterclockwise it's clockwise the resultant torque. So I can say that my vector torque is 8.92 newtons meters clockwise, right? So I found the resultant torque, okay, with respect to the origin, or with respect to the z-axis that is passing through the origin and is out of the page, right? So this is, how we solve this problem. This is a problem where, we're using the definition of torque that we have learned, okay? So well, with this exercise, we finish this video. Thank you for your attention.